Welcome back to the Foundry by Forge College. If you recall our last explainer, we dug into the trade-offs between centralization and decentralization. Well, today we're taking that theory and pulling out the engineering blueprints. This explainer is all about performance, security, and scalability impacts, which fits right into our blockchain fundamentals track on consensus mechanisms and Byzantine fault tolerance. So are you ready to see what mechanically happens when the theoretical rubber actually meets the road in blockchain architecture? Let's get right into it.
We all know decentralization disperses power, right? I mean, that's the whole philosophical dream of Web3. But as a systems engineer, you can't just run a network on dreams. You run on code, physics, and hardware. So what exactly happens to your speed, your security, and your scalability when you crank up that validator count from, say, 5 nodes to 5,000? Spoiler alert, it's definitely not a free ride.
Here's our blueprint for today's explainer. We'll start with the cost of decentralization, then compare throughput versus latency, look at expanding the attack surface, hit some scalability bottlenecks, explore real-world network archetypes, and finally, dive into the math behind the magic.
All right, Section 1, the cost of decentralization. Let's look at some concrete system costs.
Let's start by translating our theoretical understanding of dispersed control into something we can actually measure. There's an inescapable, mechanical reality to decentralization. While adding more validators absolutely increases the resilience and the fairness of the network, it physically forces up the communication and state replication workload. Every single new node you add is just another mouth to feed with data, and another voice that needs to be heard before any decision is finalized. You don't get censorship resistance for free. You pay for it in computing power and network chatter.
Moving on to Section 2, speed, throughput versus latency.
Now, we really need to unpack exactly how this validator workload affects the two core pillars of network speed. People mix these up all the time, but they represent totally different user experiences. First up, we've got throughput. You could think of throughput as the aggregate volume of work the entire system can accomplish over a given time frame. It's basically the size of the pipe. How many total transactions can the global network process, verify, and finalize per second? This is all about the sheer muscle and capacity of the whole machine working together.
Latency, on the other hand, is highly personal. This is the time a single user spends waiting for their specific transaction to be officially locked in. It's that agonizing time you spend staring at a spinning loading wheel on your screen. So you could have a network with massive throughput, but if your individual latency is 5 minutes, well, that network is going to feel incredibly slow to you.
To deeply understand why latency spikes as we decentralize, let's compare these two mechanisms. First, look at an O of N dissemination model. This is essentially like a teacher making an announcement to a classroom. It's a simple, highly efficient downward flow of info. Super fast, but yeah, very centralized. Now contrast that with an O of N squared all-to-all agreement. Imagine a massive group text message where everyone has to reply to everyone else just to decide on a pizza topping. If you've ever tried to coordinate dinner with 50 people, you know exactly why high validator networks take so long to reach consensus. The messaging overhead scales quadratically.
All right, let's turn to Section 3, expanding the attack surface. Shifting over to security, we have to look at how this ever-growing web of validators changes our vulnerability profile. Because as you know, security isn't just some simple linear scale where more nodes equals bulletproof perfection. We aren't just building a thicker fortress wall, we're actually adding more doors to the building. Upping your validator count definitely gives you higher resilience against being locked out if one node crashes or goes rogue. But it also means way more network links, incredibly diverse software stacks, and exponentially more potential bugs for a clever attacker to exploit. You're distributing the risk, sure, but you're also significantly widening the net of potential failure points.
Which brings us to Section 4, hitting scalability bottlenecks.
Eventually, all those extra doors and massive group text chains start hitting the cold, hard limits of physics and engineering, because every single node has to validate every single transaction in a fully replicated ledger. Horizontally scaling by just adding more nodes might improve redundancy, but it slams right into absolute barriers. We're talking about network bandwidth bottlenecking from the sheer volume of message exchanges. We're talking about CPU limits as every node runs exhaustive cryptographic verifications. And of course, storage limits because every node must maintain the entire globally replicated state. You literally cannot just add an infinite number of computers and expect infinite speed. At a certain point, the CPUs start sweating.
Let's look at Section 5, real-world network archetypes.
Let's ground all this theory in reality. In Forge College's advanced architecture programs, we see that if we look at the landscape of real-world deployments, distinct archetypes naturally emerge. based on these exact bottlenecks. First, we have permissionless chains. These embrace hundreds or thousands of nodes, accepting huge latency, often seconds or even minutes, just to achieve maximum censorship resistance. Second, we have permissioned consortiums. They restrict validators to a tight group of, say, 5 to 50 nodes. They still use that intense all-to-all messaging, but because the group is small, they can hit lightning-fast millisecond latency. And finally, sharded designs. These partition the network into distinct subgroups to break those horizontal scaling constraints, which allows faster aggregate throughput without forcing every single node to process the entire global state. It's all about making deliberate, calculated compromises.
Now for Section 6, the math behind the magic. We don't have to just guess at these compromises. To prove this isn't just theory, let's put these deployment choices right on the test bench using a concrete Python consensus model. We're going to set up a dramatic but highly realistic comparison. What actually happens to our effective transactions per second if we take a network running a streamlined 5 validators and suddenly scale it way up to an open, decentralized 500 validators?
Well, the output from our mathematical model shows a pretty brutal inverse relationship. As the validator count spikes from 5 to 50 and then to 500, the message overhead triggers a massive latency penalty, and our effective throughput absolutely crashes. The network basically spends so much time talking to itself, waiting for verifications, and passing messages across the globe that the actual rate of finalized transactions drops right off a cliff. The coordination tax is a mathematical certainty.
Which brings us to a really foundational engineering philosophy. Model-driven architecture ensures defensible design choices rather than just relying on optimistic intuition. This kind of mathematical modeling is absolutely crucial because it allows engineers to predict realistic throughput and latency limits before writing a single line of expensive production code. Trust me, you don't want to promise sub-second finality to your users, only to find out that bandwidth constraints make it physically impossible.
Let's wrap things up with Section 7, Conclusion and Key Takeaways. Let's roll up the blueprints and summarize the core principles of this explainer. What are the key things you really need to take away and apply to your own Web3 projects? Well, here's your cheat sheet. Number 1, decentralization lowers effective throughput and raises latency. It's a fundamental trade-off for fairness and resilience. Number 2, more validators broaden the attack surface. You eliminate single points of failure, yes, but you introduce a massive diversity of network links and software that you now have to secure. And number 3, sharding and Layer 2s offload global replication costs. If you want to scale a highly decentralized system, you simply must adopt patterns that prevent every single node from having to do all of the work simultaneously.
Which leaves us with a final, provocative question for you to ponder. Based on the exact needs of your users, what specific consensus architecture will best serve your next decentralized application? Thank you so much for exploring these engineering blueprints with us today. We highly encourage you to visit forge.college to learn more about this subject and discover an entire library of incredible Web3 learning resources. I'll see you next time.